Hello guys, welcome to this PyTorch tutorial actually, and in this tutorial we'll see how to train an LSTM classifier on the Amazon reviews dataset. So first let's create the conda env and we'll call it torch dev for now. Maybe I'll add something else. We would like 3.9 please. And yep, we activate this env. Let's make a data folder and then we'll download the required data files. Style transfer, okay, yeah, there you go. We need this guy. So I'll simply paste it, and if we change this to, so now we should have both the files. Yeah, this definitely seems like it downloaded up. Okay, so this is the dataset. Should not be very unfamiliar to you. Alright, so let's get started. So we'll start with reading those files and creating a dataset for ourselves, and we'll create a train, validation and test split, which is going to be an 80-10-10 split. Not here. So it receives a path. So this function will receive a path and it will return us all the lines in that text file. So file path as f, and it returns all the lines. Now let's implement something called prepare dataset, and what it will receive is a data directory, and then pos path is going to be os.path.join data directory plus pos.txt, and the same thing for negative file. Now these, to get rid of these squiggly lines, let's import os. Okay, so now we have the pos path, now we have the negative path, and pos lines would be read text file, pos path, and well, we'll have something similar for the negative counterpart. Okay, so we should have all the lines now. All right. Let's actually see if this works. Okay, so if name equal to main, standard Python stuff, we'll create a main function. And for now, this prepare dataset calls it from this data directory. Let's see if this works or not. Oh, seems like it did. We should print something probably. Okay, yeah, I was too fast to rerun it. So cool. So it has 400,000 lines, as it should. So let's now proceed to creating, like, tokenizing stuff and whatnot. So in our case I will not be using NLTK. I'll keep it simple, and we'll treat we'll treat every token that's delimited by a space to be a new word in our vocabulary. So that's quite simple to do, I guess. And for line in POS lines, let's create a sample. So this sample is going to be, first of all, the line itself, and then we'll also add the label to it. So we know this is positive class, So we added that. Cool. Yeah, just making sure it was recorded. And we'll do something similar for the negative part. Instead of POS, it's gonna be negative. So now dataset should have 800,000 lines. And let's do some, minimal text processing here. Oops, something happened. Let's lowercase everything and then strip them as well. Lowercase and strip them. And let's now also quickly create a vocabulary for our downstream task. And so that vocabulary is just gonna receive these lines. It's just gonna receive all the sentences in our data set, and then it's gonna create a vocab for us. So let's call this function create vocabulary, and it receives lines. And I guess I should have, yeah, I can pass the data set here and create vocabulary lines, or we call it a corpus. We can also call it a corpus. So looping through all the lines. First sample in lines, we know that text is going to be sample.split at this, since we added this extra tab here. So now we have the text, and then in this text we are going to we'll need to maintain something called word to index, right? And let's also maintain, well, let's see how it goes. For word in word to index, actually not word, for word in text dot split. So this is my tokenization, literally split is my tokenization part. So if I'll see if this word is not in word to index, I'll add it basically. This of word, and we need to start with an ID, right? So what we can do to build it dynamically is just get the length of the current dictionary, and then use something like this. And what it returns, this function in the end, is word to index. So the total number of words that we have in this dictionary, or the total number of keys that we'll have in this dictionary, that's going to be our vocabulary size. And let's actually check out what the vocab size is. List has no attribute. Oh yeah, my bad. It should be this. Okay, so this is our current vocab size, and as you can see, it's quite huge, like 283,256. Yeah, not so good. So if you try to train something with this high a vocab number, you're not gonna be able to train anything probably. So to fix that, we can what we can do is introduce something called minimum frequency. So words that only that occur at least the minimum frequency number of times in our data set, in the corpus, we'll only be retaining those words, otherwise we'll not. And in order to filter out such things, we will we'll also need to maintain something called word to count, later on to filter stuff. Oops. And it will be initially empty. And if a word was not originally there, we can simply initialize it to be 0, or no, sorry, 1. Else, if a word already exists, then we only need to increment the counter here. Now, once we have this, we can do something like, actually we don't need to, so we don't really need to create this guy here. Yeah, we won't need to create this guy here. We can do it like after we have built the counts. So for word in, word to count, actually let's try to be a bit more efficient. For words counts in this, if C is greater than or equal to minimum frequency, word to index of this word is going to be length of that, length of word to index. And I think that should be it. Let's see what's the vocab size now. Oh, create vocab is missing, obviously. So let's say the threshold is 10. So anything that occurs less than 10 times in our dataset, that's going to be removed. And whoa, it's like a 10-fold decrease, right? So from 280 something thousand, we went from there to like 29,000 something. So this still looks okay, but we can do something more. So let's try to further remove some extra stuff. And while we are doing that, let me do, let's install this pip install. So these are two different packages, just telling you. Black is something just that I need for my purposes. It's not required. And so this is what black's gonna do. It's gonna format things for me automatically. So now that we have this, this function should return the dataset that we have. Well, there are a lot of issues with our dataset. We'll fix them later. Dataset is equal to this and print. Oh, my bad. Oopsie, I should have printed just a few of them. Cool. So these are the top 10 sentences in our dataset, and as you can see, so this is our sample basically. So this is the sentence, this is the label associated to it. Now, there will be some instances that we can optimize upon. So for example, if there are, there's something like this, or there are some other occurrences like that, we can take care of these guys by writing something to normalize text, and it will receive a sentence. So X here is a sentence, and first of all I'll get rid of all the, well, I'll need to import this too. We'll need regex for this and Unicode data. Let's first actually write this function. So when you are dealing with raw text files, it's always possible that some weird symbols sneak in. So all I'm doing here is normalizing normalizing those special guys. You don't need to do this. I guess you were doing something more special. You were anyways asked to remove those special characters in the assignment, right? So you can ignore this part. This is just for me, this is like a hacky way for me to take care of some things, because I don't want to implement a complicated tokenization here. So what we will be doing in this one is, okay, I guess if so we'll replace the occurrence of these guys with whatever's inside, and anything that's not, oopsie, so we'll just replace them with a space. So this is gonna get rid of some weird characters that might sneak in. So instead of this, what we can do is line is normalized text of line, and then we can simply pass the line here, and we can do the same thing for the negative part. And this tutorial might be a bit long, so feel free to skip to the part that you actually care about. And let's see if this makes any difference. I should add some print statements. So you see, when you added this normalization part, it's taking longer because it's running that thing. So yeah, now you see that, you know, from 29,000 we were able to go down to like 23,000 or 24,000 actually around. This is still a bit higher, but for our purposes it should be okay. It's not too bad, because we'll be implementing an LSTM classifier which will be not too deep, and yeah, we will see. Preparing dataset and processing positive.txt, and you know, so that we don't process all those 80,000 something lines again and again. At some point I'll truncate the dataset. Okay, so now we have a way to, so now we did two things. We removed anything that's below this minimum frequency in our dataset, in our corpus. So while we did that, so we only did that, so we only removed those things from our vocabulary. However, we did not like actually remove those words from the dataset. So when you pass these things, and something that's not in the vocab appears, as it will, we will need to handle that. And to handle such special cases, we will add some tokens to it, some special token. We will introduce some special tokens in our vocabulary. I'll get back to that later. Yeah. Or maybe I can just add them here. Let's just do it here. Word to index. Yeah, let's just do it. So for any NLP task, there are four. There are usually, like, there can be more than four, but usually you'll find these four special tokens. It need not exactly have like this value, but there's a token usually to represent the start of the sentence, the end of the sentence. The padding token, we'll see why we need that, and then there's this unknown token. Okay, so we'll see where these guys actually come in handy, and we'll get rid of this, we'll get rid of this as well. So now word to count, blah blah blah. Cool, so we should be good. So now we will be able to handle things that are not in the vocab but in the sentence. What we'll do with the with those guys, we'll just replace them with this unknown token, but we'll get to that. Before that, we actually need to create train, validation, and test split. So before that, we also should shuffle the dataset. Oh, there's no numpy. And I'm surprised there isn't. Oh, it's already there, it's just not detecting. Interesting. Does it work? Well, it does work. For some reason, the env is not updated. Yeah. So here what we'll do is we'll shuffle the dataset, and we'll create the train, validation, and test split. Oops. This is the vocab size. We can print this. All right. Create train, val, and test split, and it's, as I said, it's going to be an 80-10-10 split. So let's whatever the length of the data set is, that multiplied by 0.8. Well, in our case, we know that it's going to be a whole number, but just in case it's not, for data sets it's not. Okay, length of data set 0.1, and now the train part is going, let's actually let's actually create a dictionary for our data set. And what this dictionary is going to look like is, so the first n train samples will make up for our training set. The next n val examples after that will make up for the validation set, and whatever remains, that will make up for our test set. Okay, and we are returning this data set now. So now we should be printing, let's see, what's the dataset size? Length of data set. This is the size of the training data set. This is the size of the validation data set. And hopefully they should match the numbers that you might have seen before. Okay, time to truncate this. Okay, so yeah, 80% of 800,000 is this, and 10% of it is 80,000. So it makes sense. Now it's time to, you know, truncate these guys. I don't want all the 80,000 lines to be pre-processed every time we want to test something. So This is gonna speed it. So this is just temporary. I'll remove it later on. This is just just so we can, you know, train things faster. And let's also return the word or the vocab here, right? Or let's be explicit and call it what it is. It is word to index. And why? Okay, so another reason why do we actually need to map a word to an index is that's because you know, our models cannot process these raw texts. So what they understand are these values. So eventually what we'll do is we will convert something that looks like, you know, let's say I like this I like this room to something like this, where these numbers represent the index of every word in this word to index or in our vocabulary, right? So yeah, that's what this indicates, but we don't have that thing yet. Now let's actually, this should be it for the dataset preparation part. So let's actually move all of this to another file. Let's call it utils, and from utils I'll import prepare datasets. That's all we need. So this is what I should have told you this earlier, and I did in the in-person tutorial, but anyways, so this is our raw data. From here we want to pre-process it or pre-process it, and then we need to convert these into indices, those tokens I showed you before. Then we'll feed them to the model, we'll get some predictions, and we'll optimize a loss against you know, some ground truth. And that's what we'll do in the end. So what we have right now is sort of this, and we want to basically implement this training pipeline. So there are I mean there are multiple ways of doing this. What we can do is, now that we have a data set, we can create you know, we can manually create batches from these objects, and then we can simply loop through those batches. So one example would look something like, for batch in dataset train 64. Yeah, so this is basically gonna, so if 64 is our batch size, then it's gonna create a batch of 64. So this batch length is gonna be 64. So this is one way of doing it. However, when we are writing code in PyTorch, or when we want to write it in PyTorch, then there are some utilities that we can use to ease in our lives, to add some efficiency, computational efficiency to it, and we can do that by using the dataset and dataset loader classes that PyTorch provides. So so basically what we'll do is we'll create a dataset class for us, Amazon reviews dataset, and this guy needs to inherit from this guy. I think it's torch.utils.data.dataset, if I'm not mistaken. Let's actually double check. Torch, okay. This is what I usually do when I have any confusion. Dataset, right? Yeah, torch utils dataset. Should be good. So when we implement our own custom dataset, then we actually need to implement, or rather overwrite, these three methods. So one is the init, or the constructor of this class. The other is get item, and the last one is len. So I mean, these three methods, they exist for every other Python object. So whenever you do something like, you know, so first of all, whenever you create an object, this method is called, it's the constructor. And whenever you do something like, let's say for a list, you do something like a of 0, you're trying to access the 0th elements, then for this list, this get item method is triggered under the hood, and this length is triggered when you want to get the length of that object. So for example, when you do, if a is a list and then you do length of a, then this length inside the list class will be triggered. So now we'll simply, so what we'll do is we'll wrap the different training parts that we have here to this, and we'll see. Yeah, so the constructor is going to receive the data, and yeah, it's going to receive the data set, and basically this is what we need to, length can be we can simply return self data cool. So whenever we do something like, you know, length of whatever training data sets we have, this is going to be triggered. And yep, okay, so let's this is the interesting bit, I guess, at least the beginning of the interesting bit. So, you know, we can actually trigger this. Train part is equal to dataset train, and let's try to wrap this thing around the Amazon reviews dataset that we have here. And okay, Python, yeah, let's see. And yeah, you can ignore this vocab size. This is only because, you know, we are processing just 200 lines in total, and we'll fix this later on. This is just for debugging purposes. Okay, interesting. Oh, I see what's the problem. Word to index. So remember, we changed the signature, so now we are also returning this guy. Let's try to rerun this. What happened? Well, it executed without an error, and so okay, so as you can see, this thing was not triggered, and it's only triggered when you try to access something. So this get items triggered. Okay, so now now we are in, and let's see. So this is what the sample looks like that we have currently in our dataset, right? So notice this extra tab here. So what we will be doing is we'll convert this this thing to a list of indices, and all that needs to be done inside this get item, so that when we, you know, we loop through this dataset and we try to access the ith element, what it returns is yeah, the things that we need, like the label, the token IDs and stuff like that. So in order to convert this into those token IDs, we will need to pass the word to index dictionary here as well. And word to index, sweet. So from this sample we can extract the text and the label as follows. So if we remember, we were splitting it as a tab, right? So when you split it, you'll get two elements. The first element would be the text, the next element would be the label. So right now the label is going to be a string, so let's convert it into an integer, right? And then for this text, so let's implement something called text to indices or something like that. And let's move this guy up here, and we can add that method here. We'll call it text to indices, and what it receives is some text, and it's gonna return, it's gonna run that word to index dictionary on top of it, and then it's gonna return us an ID'd form of that guy. So for word in x.split, so x here is a sentence, remember, right? It will be a sentence. For word in x.split, what we'll do is we'll simply word to self word to index of word. Let's try to do input IDs, and input IDs is self.text to indices of text. Cool. Let's see if this works or not. And let's get rid of this guy, this guy, this guy, bye-bye. So you see that we ran into this key error. So this basically means that still doesn't occur enough number of times in our dataset, so we ended up removing it. You remember we had this threshold, we have this threshold of 10, so things have to occur at least 10 times in our dataset for them to be considered in our vocabulary. So how do we fix this? So for this precise reason, we added these special tokens. Where did it go? Yeah. So anything that's out of vocabulary, we'll replace that with an unknown token. And that's exactly what we'll be doing here. Okay. So unknown ID is going to be self word to index of this unknown token. And now we'll change this to .get w unknown ID. So if something is out of vocabulary, so if it returns this key error, then it will assign unknown ID. It will append unknown ID to this input IDs, and now it should be fine. Let's see. Let's hope it works. If it doesn't, we'll see. Why not? All right. Input IDs. Oh, it doesn't exist yet because this hasn't been executed. So you see all these trees, they're basically all these trees, they're basically the unknown tokens, because that's what the and it will be more apparent if I guess we also build text. Yeah, let's also maintain some text, updated text. We can actually initialize both these variables here. Text. Now to this text, what we'll be doing is, okay, cool. So first of all, we'll get the token ID. So the token ID is going to be self word to index of this word. actually this thing, the exact same thing. And if this token ID is equal to unknown ID, which means that it's an out of vocabulary word, to input IDs we'll append token ID. Well, in any case we'll be appending this. We'll append an unknown token here, and in cases it's not, okay, let's try to be explicit here. Oops. Else text dot append that word. All right, let's also return this text. Let's call it, so this, since this is like a clean version or an alternative version of this guy, let's call it underscore text for now. And let's see what this looks like. So as you can see, anything that was out of vocabulary, it has been replaced by an unknown token. And there are a lot of unknown tokens here because, you know, like the vocab size itself is too low. This is going to be fixed when we run this on the full version of the dataset. Okay, so now we have some things that we need, and we can now return this. So we can go with a tuple, like we can I return something like this, but you know, tuples are always less readable and they're also immutable. So we'll go with a dictionary here. So we'll update the we'll return the actual text that will be seen by the model in the end, like whatever the input might have been. This is the text that the model is going to see, and these are the input IDs. And next we'll have the label. Cool. So we can okay, cool. So now that we have that, let's try running this. So now you see what we get is a dictionary instead of just a sentence, right? So we get, actually we need to fix something. So this should be a string. Okay, now it should be a string, yeah. So okay, so now there are some things to note. Actually, let's go a step ahead and create the actual data loader. So to create a data loader, what we need to do is to wrap this data set that we just had inside. I think it's the same correct API call, torch utils data dataset, torch utils data loader, and what it accepts is a batch size. So let's say the batch size is 64 in our case, and there's an additional argument to decide whether we want to shuffle it or not. We'll not go with that for now, and let's see what the and actually let's try with a lower batch size first. So now since this is gonna be a data loader object, we cannot simply do a print on top of it, so we'll need to, so now we can yeah, so we ran into some issues here, right? So that's because unlike in computer vision, in text we have sentences of variable length, so the sequences can vary. So when it was trying to, and what happened right now here is it was trying to give us a batch of 10 sentences, but in order for it to work, all the sentences must be of equal length at least, right? So, and this is a general problem in NLP, like practical issue in NLP, so you'll probably not see this in the papers, but whenever you implement something that deals with text, you have something of a threshold. So that threshold decides like what's the maximum length of a sentence in your data set. So for example, like there could be a sentence that's 100 tokens long in your data set, but you don't really care about that, even if so you just truncate it to, let's say, 30 or 40, because that will cover, let's say, your maybe 90-95% of the data set, and it's not really a bad thing, because you'll not be losing out on much. And especially for this task, like this is just a binary classification task, so if for one data point for like just one class out of 400,000 you happen to truncate some information, it's not gonna be too bad. So let's implement that thresholding here. So we'll decide, let's say, the max length of the sentence in our data set. It could be 20, 25, let's go with 25, or maybe we can play with this as much as we want. So now that we have this parameter, you might guess that some sentences will exceed this threshold, some will be shorter than this threshold. So what do we do for these guys? So for sentences that are longer than this length, we truncate them. For sentences that are shorter than this, we pad them. So that's where this guy comes in. And whenever you're training a NLP model, you add these two special tokens to tell the model like which part to focus on. So for example, if your model is trained well enough, then it's gonna ignore anything that comes after the EOS, because otherwise it's not gonna know. There's no way of telling the model to focus, there's no way to tell the model like which part to focus on, right? So for example, if your sentence goes like, I like blah 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 blah, and then you don't have the EOS token, and then you have a bunch of padding tokens, so how will the model know that it doesn't have to process these guys? So for that we need a marker, and that's exactly what this EOS token is. And similar logic applies for this SOS token. So anything that's between these two guys, the model learns to focus on only these and ignore anything that comes after that. This is, I guess, a bit peculiar to the NLP field. So let's implement this. So we'll need to add this guy here. So whenever we are so similar to the unknown ID, we'll need SOS. Here it's gonna be EOS. Here it's gonna be the padding token, because now we'll be needing all these guys, and you'll see in a moment why. So we'll need SOS because that's what we'll initialize the input IDs with, and then we'll also initialize the sentence with SOS tokens, not OSS, SOS tokens. And and here's where we are gonna add that check. So if length of input IDs, if length of this is greater than max length sentence dot, then what we will do is we'll input IDs is equal to input IDs self max length, and we'll do the same thing for text, right? Because until now, like, both of them are just lists, right? This text being a list of strings, this input IDs being a list of integers, right? So now what to do with those that are shorter? So in this case, we'll pad. So here we are truncating, here we are padding. So how much to add? How much to pad? How many padding tokens to add? That's what we'll decide right now, and it's quite easy, right? Whatever your threshold is minus whatever the length of your input IDs is. So I mean, basically you're missing these many tokens for your batch to be of the same size. Cool. Now what we want to do is add this guy. So we want to add these many padding tokens. Oopsie. These many padding tokens to text, and okay, and these many padding tokens to the input IDs. All right. Oh, by the way, I forgot to add the EOS token. So once we are done with this, we will add the EOS token, and instead of this, it's gonna be the EOS ID for input IDs. Oopsie. Okay. All right. And we need to do something similar, but here we need to do this before adding the padding tokens. Otherwise, like, what's the point? So if we do this after padding, then it's gonna look something like ABC, and then some padding tokens, you know what I'm trying to write here, and then some EOS token, and we ideally want to ignore these padding tokens. So we add the EOS before, and then we add the padding tokens. Hopefully this should be okay. Okay. Let's see if this works or not. Init is missing, of course it's missing something. Yeah. So here, let's say the maximum sentence length is 30 in our case, or to actually show you the effect, let's go with something lower. Each element in the list should be of equal size. That's true. I feel you there, but what's the issue? Let me take a moment. Okay, so I figured out the issue, and the issue was quite minor. I needed to add this guy here instead of doing it there, because, you know, if otherwise it's gonna mess up with this calculation, right? Because we are adding a token we don't want to consider. So now it should work. And I added this to debug. We don't need it anymore. So this is how it's gonna look like now. I know it looks ugly, sort of, but what I want you to focus on is this part. So as you might have seen, this method was implemented for just one sample, but since we wrapped this dataset inside this data loader, it's gonna apply that operation on this batch of size, 10. So that's why you see this, and right now it's a list of tensors, but let's make it a tensor, not a list of tensor, because that's what our model will understand. So now it's a tensor, right? Cool. This is by default a tensor. Okay. Is there anything else I'm missing? Nope. Oh, by the way, yeah, one thing about this random shuffling is try not to use random.shuffle. I've encountered some issues with it in the past, like its behavior is not very trustworthy, so just stick to numpy's random.shuffle. So I think here we are done with the data loading part, and let's move again all this clutter inside a different file. Oops. Yeah, let's move this somewhere else, and that somewhere else, let's call that somewhere else dataloader.py. Okay, and let's also add a function here. Let's also add a function here which says make data loader. What it will accept is a data set. It will accept a data set, it will accept the word to index, it will accept the max sentence length. I mean everything that our data set requires, like everything that this constructor requires. In addition to that, it will receive a batch size, and what it's gonna do is it's gonna make, first of all, an instance of this special custom dataset class. You know, there's a better way of doing this, but I'll not discuss that here. It might be too magical for now, and it's not data sets. And what it will do is it will return utils.data loader of this data set, batch size this. Now here what we can do now is so this is our training data loader. Oh, I see. We can, let's also import from data loader, import make data loader of data set of train, and what's the word to index. Max sentence length is, let's set it to 30 right now, and batch size is 64. Let's go with that, and we'll do this for the validation as well as the, and yeah, mind you, like this can all again be written in a much more nicer way, but we're going with this for now. And let's see if we are able to see the first training batch. Oh, let me also take a moment. It works. Let me also take a moment to show you why this guy is needed. So when you include this, whatever you have written here, it's only going to be executed when this script is called, like this module is called as a script. However, if you don't have this line, let's say you don't have this line, then it's going to be called every time. This function is going to be executed every time a different file, a different submodule imports from main. Let me show you how that works. Let's say we have this data loader, right? And let's just call this data loader here. So let's make a dummy function. My bad, I don't want to create print called and yeah. So if we execute this, this thing was called. So it basically means that this function was executed. However, we don't want it to be executed if we are importing this data loader. So to avoid that, we add this thing, and now it should not, and actually let's also not print this. So now you see that called was not printed even though we are calling that thing here. So this is the difference between including those lines versus not including those lines. Hope that answered questions for some of you. Okay, so now we can actually proceed to writing a training loop, because we are here right now. So we have the raw data, we have the pre-processed the data, converted them into indices. Now we want to just pass them to a model. And let's start our model implementation. So whenever you're implementing a model class, let's call it LSTMClassifier, and you have to inherit from this guy, torch.nm.module. Okay. And can I magically initialize this? Yeah, looks like it. Okay. Sorry. LSTMClassifier self. So this is the initializer and forward method. So we'll see what these guys do, how to use these guys. Okay. So now that we have a data like a batch, so this is our batch, right? And our model is this guy. So whenever you do model of batch, this forward function is called, and this is equivalent to doing a forward pass on your data, right? So that's how PyTorch is implemented. So this line is exactly the same as this line. So I mean, except you don't really need to explicitly write that forward. Whenever you call a batch on something that inherits from torch.nm.module, it automatically executes the forward thingy. So now in this model of ours, what we will be having first of all is an embedding layer. Torch.embedding. So okay, as you can see, the documentation says that the first argument is the number of embeddings. So in our case, it's going to be vocab size, right? And the second dimension is the embedding dimension. So what's the embedding dimension for our use case? And that's it for now. I guess that should be enough. And let's also feed these guys. And before I move forward, let me explain why we need these embedding matrices or this embedding matrix. So think of this embedding matrix as a lookup table. So for every word in your vocabulary, it's gonna so here's what our input IDs will look like, right? It's gonna be an input like something like this, except it's gonna be a batched version of it. I'm just showing one sample for ease. So when you pass these things to these input IDs as is to the model, it's essentially equivalent of using one-hot encodings, except you're not exactly using one-hot encodings here, but it's sort of similar to doing that. And the model is basically gonna have a hard time relating between these two random numbers, right? how does this word correlate, this token correlate with this token. So what we do is we project each of these tokens into a higher dimensional space, and that higher dimensional space in our case is the embedding space. So every element in this input ID is now converted into a 3-dimensional embedding for 300 dimensional embedding for 34, and so on. So initially if your input IDs was batch size by whatever the max sentence length you had, let's call it t, then after running it through the embedding layer, it will be whatever your embedding dimension. Oh, I wrote 300 because in the back of my mind I have 300 as my embedding dimension. So if your embedding dimension is 300, you go with that. And that's exactly what we are gonna do here. Let's pass. So we'll be passing this batch through it, and we know that this batch is a dictionary. So embedded is equal to self.embedding layer of x of input IDs, and let's intercept this call and look if it works or not. Of course it's missing two things. One is the vocab size. So vocab size is going to be length of word to index in our case, and embedding dimension, since I had 300, let's go with that. Or actually let's start with 100, it's not gonna hurt. We want things to move fast. Okay, so now if you look at the embedding's shape, it's gonna be batch size by your max sequence length by embedding dimension, and what it looks like is something like this. You cannot really make much sense of it, but essentially your input IDs, oopsie, x input. So you had these let's just consider, so for each of these guys, so for 0 it pulled out 100 dimensional vector. For 0 it pulled out 100 dimensional vector for 4, and so on, and that's why you have that extra dimension here, right? So this extra dimension is because of that. So now that we have our embedding layer, we actually want to pass it through an RNN, right? So in our case, this is going to be a simple LSTM. Oopsie, torch.nn.lstm, and although it doesn't say here, let's look at LSTM. Yeah, so if you read through the documentation, you'll see the first one is input size, the second one is hidden, and the third one is num layers. That's what we will need for now, but you can see that there are other things, like if you want to make this a bidirectional LSTM, you can go with this. If you want to add dropout to your network, you can go with that, as you will be required, I guess, to experiment with. But yeah, so in our case the input size for the LSTM is going to be embedding dimensions. So basically when you embed it, when you fetch the embeddings, now you'll pass this thing through the network and get the feature vectors, like the feature vectors for the sentences, and the output dimension is going to be hidden dimension, like how many hidden units do we want to have, and then oops, number of layers. We are not currently accepting any of those guys. Let's fix that. Let's say, what, we'll go with 300, and then let's say it's a 2-layered network. Right now, okay, so right now what we have is embedded. So it's a batch size by t by embedding dimension, and we want to pass this thing through our RNN. Oopsie. Voila. So now we have the outputs from the RNN. So what does an LSTM output? Let's look. So this is the input, these are the outputs. So it's gonna output, so it's gonna return us 3 things, as it should. So LSTM returns you 3 things. One is the output, HN, the CN. So let's talk about them for a moment. So HN and CN, these are hidden states and cell states respectively. And output, as you can read here, contains the output features from the last layer of the LSTM for every time step, right? And HN is basically the final hidden state for every element in the sequence. And as you might see, this is the only thing that, you know, depends on the number of layers, right? So for classification tasks, what we use is the outputs, because that's what we care about, right? So we care about the output of the last layer. It's similar to, I guess, even vision. Like, even if you have some kind of a CNN, you pass your model through your CNN, you get your features from the last layer, and then you use those features for like classification, right? In the end, you get the logics and then you make classifications. Here it's a similar idea. You use outputs for classification, but when do you actually use these HNs and CNs? These are for encoder decoder type tasks. So when you want to actually get the latent vector for a given sentence, you actually use HNs. And cell states are mostly like they are very less likely to be used by anyone, but it's still useful in some cases. Like when I personally tested to see what CN like helps with, it does help in some cases, but you know, HN is anyways more helpful. So for all practical purposes, you can ignore this cell state and focus on HN and output, and remember that we use output for classification tasks and HN for more sequence to sequence like tasks. With that being said, so that's what our output is going to be, and we can ignore whatever is the rest. Okay, so as you can see, we went from the embedding space to the model's hidden space, right? So so the embedding space was 300 dimensional, the model space is 512 dimensional as we specified here. So now what we actually need, you know, is something like this. So this is what we have right now. We have something batch size t and hidden dimension, but what we actually seek is something like a feature vector on top that we can use to you know, compute logits. So you see, logits are batch size by number of classes dimension. So they are basically, they have as many elements as you have in the as number of classes you have in your dataset. In our case it's 2, so in our case the logits are gonna be like of length 2 for every input sample. So we basically need we need a way to go from here to here, 2, because we have only 2 classes. So we need to do 2 things. First of all, we need to get rid of this extra dimension, and then we'll need to project this from, you know, 512 dimensions to just 2 dimensions. Now how do we actually get rid of this guy? So what we do essentially is we only look at the we only consider the output representation of the last token in a given sentence. And why do we do that? Because when we train RNNs, since they have a feedback loop, we hope that the representation for the last token in a given sentence, it also contains information about its past, that is, and all the tokens from the beginning, and that essentially can be used as a sentence representation. So it's essentially going from a token representation to a sentence representation, right? And let's ignore that. So how do we extract the embedding for the last token from every element? Well, it's quite simple. We just need to do this, and this is what it looks like. So what we essentially did here is tensor slicing. So you know how we have a list, let's say we have a list 1 2 3, and if you do something like this, it's not going to slice it, right? So this is like doing tensor slicing, but on every dimension. So we know that output is initially 3-dimensional. So doing nothing on the first dimension, we need everything from there, but from the t dimension, we only need the last one, that's shown by -1. And from the third dimension also we need everything, but since this is occurring after this, we can after this guy, we can ignore this. So these two guys are like equivalent. You can play around with this to understand more, but yeah. So we went from BST hidden dimension to BS hidden dimension. Now we want to actually have a projection. Let's call it the output layer. So this is going to be a linear layer in our case, the input being hidden dimension, the output being number of classes, right? So we don't have the number of classes as input yet. And classes. Okay, 2 layers, 2 classes, and essentially this is going to be my output. So when you pass a batch through this model, this is what it's gonna return. This is what it's gonna return. So this thing will be batch size by 2-dimensional. And let's look at this guy. Yay! The shape of this is batch size by 2. Okay, so now we have the forward method implemented, and so let's actually move on to write a training loop here. Okay, all right, so we have these 3 data loaders. So first things first, here's our, we already have our model. Now we want a loss function. So loss function we will be using is cross entropy loss. Then we'll need an optimizer. It's gonna be torch.optim. Let's go with Adam. So what it's gonna accept is the model's parameters. So that's what will tell like which parameters to optimize later on. And learning rate. So you can see the documentation here. Params, learning rate. Yeah, params, learning rate. So by default it's 1e minus 3, but let's be extra explicit here. And so later, so what we can do later on is, you know, move all these hyperparameters to a common file called config or whatever, and then we can read these hyperparameters from there instead of, you know, hard coding it here. But this is a tutorial, so I'll not do that here. So we have the model, we have the loss function, we have the optimizer. Now what to do? Now we can actually move forward to writing a training loop for batch in training data loader. So here's our logits. Logits are gonna be model of batch, and from these logits we calculate the loss first. So the loss is going to be calculated, okay, against these logits and whatever the ground truth labels are. So let's fetch the ground truth labels too. What did we call them? Label, I guess. Yeah, we call it label. And we have the loss, and once we have the loss, we essentially now can do stuff like backward. But there's something else that we also need to keep in mind here. So when we run this loss.backward, so here's what happens. Get rid of this guy. So this is your input, right? And then from input, you feed your input to the model, and then your model outputs some logits. You optimize those logits against some ground truth classes, and then you get the actual loss. But how do you make your model learn? Like, how do you pass that feedback along to the model? Well, when you call that loss.backward function, it essentially passes this feedback to first the logits, and essentially, so let's break this model too. So this model is essentially made up of this RNN. So model is made up of this embedding layer, then we have this RNN layer, then we have this output layer, right, in order. So the output of this layer is the logits, and first the loss is transferred here, the feedback transferred here, then to the RNN, then to the embedding layer. Now notice that I'm just initializing, when I run this, it basically initializes a vocab size by embedding dimension matrix. So and that matrix is by default trainable. So yeah, that matrix is by default trainable, which means that initially all the 300 dimensional embeddings that it pulls for any token, they are randomly initialized, and over time, as our training progresses, it learns a meaningful representation. Now, like, those values change to something more meaningful. All right, so with that being said, with that being said, I want to add one more thing. Well, logically you can do like a loss.backward directly, but what we actually need to do before this is zero grad, because sometimes what can happen is there are some gradient issues, so there are some lingering gradients from the previous iteration and whatnot. So just to flush out those extra junk, we zero out those guys, and then we apply this loss.backward. And once we apply, so this is gonna take care of the feed, like this is gonna provide the feedback, and then the optimizer is also gonna be updated likewise. So this is pretty much it for the training loop I guess. And what we actually need to be able to see is, I guess, this. Let's see if this works or not first, and then we can do extra stuff. We didn't see any errors, so it worked, I guess. Okay, so actually to track how much training has been proceeded, it's finished, we can do, so this TQDM, if you wrap anything around, like any iterator around TQDM, it's gonna show you the progress bar, and it's not currently in my ENV, so I need to install it. And that was surprisingly fast again. So now at least I should see, yeah, so we see this progress bar, so we know that the training did actually happen on whatever tiny data set we had, you know. We still haven't removed those 100 line truncation thingy. So let's actually print the loss values. Losses, and we'll also print the train accuracy here. Right, so we have the losses, and let's actually look at the loss. Yeah, let's actually look at the loss. That will help explain some things specific to PyTorch. So if you just do print of loss, it's gonna wrap everything around this tensor, and we don't want this. For the purpose of for tracking purposes, we only need this floating point value, so we do loss.item to give us that, and that's exactly what we are going to append to this guy. And what about accuracy? So in our case, it's going to be very easy. So we already have the logits, so how do we get the predictions from the logits? Oops, yeah, so how do we get it? We apply the argmax over the logits, and this just tells it to run it on the batch dimension and not. Let's just actually look at here. So these are our logits, and we want to, and this is what they look like. Let's look at one logit vector, right? So it says right now, well, it's a bit tricky to explain because this is not exactly softmax. So you usually, well, I'll get to that. What I want to show you is what happens when you apply an argmax operation on top of your logits. So okay, so either this can happen, which is not what we want, or we want this, right? So we want to apply the argmax on the first dimension, I mean, yeah, not the 0th dimension. So when you apply this argmax operation on every element in that batch size by n classes logit vector, you essentially get the classes, right? You essentially get the predictions. I mean, these don't need to make sense right now. I'm just trying to show you what will happen when I apply it. Now, one thing to notice here is, you know, don't apply this argmax before calculating this loss. I mean, here I'm still calculating the loss on the logits and not these predictions. That's because argmax is a non-differentiable operator. So, you know, as you saw before, I can go from here to 0, because if I get a max, like if I track like at what index I have the maximum value, I can get 0, but I cannot go back from here to here, right? So I can get the index of the maximum element in this vector, but I cannot get the vector if I just know the index, like the value of this vector if I just know the index, right? So that's why we apply the argmax. We don't, so we apply the loss on the logits. So these are the predictions, and okay, now accuracy is just going to be, in our case, this, or maybe let me see. If I apply argmax over my logits, okay, so I do need to change it to int. All right, and if I do a mean, floating point number. Okay, so instead of int, let's go with float. Okay, so I have them. mean. That's interesting. I don't need to convert this into an array then. Accuracy star append. Accuracy star append. Whatever I did here. Cool. And to fetch the element and not the tensor object. Cool. So we have the accuracies, and let's actually so after this loop, let's print the loss and the accuracy. I guess I'll need it anyways. So we want to print the mean, right? So let's import numpy after all, because I don't want to do like sum and then blah blah blah. Array. I don't think this is not gonna work, or maybe it does. Who knows? Let's try. Only one way to find out. Okay, let's get rid of the can't call numpy on a tensor that requires grad. Use tensor.attach. This is on line 55. Oh, of course, line 51. I see what's the issue here. So instead of this, I guess what we need to do is this, and because these guys are tensors, so and every tensor has a numpy well, we will it should be let's look at what's happening here. This could be interesting because this might be okay. Oh, I see. I updated some things in my head, but not in the code. Losses, and losses is what it should be, and oopsie. So so if I cannot do a mean on top of this, so what we'll do, so we'll need to switch it back, and okay, so I guess now we can switch back to what we had earlier, this np array version. Okay, except we need to do this. Let's see if this actually will work or not. Let's test it. It does work. So we can remove this, close it, and run it again. Okay, so after first quote-unquote epoch, our test loss, training loss was this, and then the testing loss was this. Sorry, training accuracy was this, 66%. But well, we need to actually wrap this inside. So this was just one epoch. for epoch in range whatever number of epochs you decide. Let's say it's 10. You print this and you print okay, epoch and what this is loss, training loss, and this is just going to restrict it to the first 4 floating point numbers, otherwise it could be, you know, this long. And train accuracy, this guy, and this guy, except not that guy. So now if you run this for epoch, whoa, see, the model literally overfitted because we only have like 200 examples. And let's now remove that constraint, this ridiculous constraint, because we I have the training loop but I don't have the validation loop yet. So let's add that. For every epoch I'm gonna have to do some validation. So with torch.noGrad, so when you do this, there will be no gradients required, and you need to do 2 things basically whenever you want to run your neural network in evaluation mode. First, disable gradient calculation and switch it to eval mode. So this is going to take care of stuff like dropout and things like that. Okay, so in your validation loop is going to look exactly like the training loop, except you'll not compute the losses. And I mean, you can compute losses, and that's how you will be able to I guess say if your model is see if your model is overfitted or underfitted or things like that. But what you don't need to do is you don't need to do this backward propagation. You can compute the loss, but you don't really need to compute the you don't need to form a backward propagation. This is going to be validation loss, and this is going to be my validation accuracy. And so the testing loop is going to be exactly the same as the validation loop, except instead of the validation loader you have the test loader. And yeah, the model obviously overfits. So actually, you know, let's write functions for these 2 guys instead of having them like this. Let's write a function for train. Definition train. Does it fix it for me? No, it doesn't. It's not that smart. So what this train is going to need is a data loader. It's going to need the model, it's going to need the loss criterion, and it's going to need the optimizer, and it should be good. So now let's call that train on train data loader and model criterion optimizer. All right, so I mean, you can actually use the same function for training, validation, and testing. You'll need an extra flag to first of all, I guess, determine whether it's training or not. But for our purposes we will just write a different function. It's more readable. And we'll literally copy paste stuff. So this is the most mundane part of, actually not this one yet. And instead of this, I'll just add a decorator. So this is equivalent to writing that with torch.nograd env thingy, but here now we have saved essentially an indentation. So yeah, that looks nicer, the code looks nicer. So we'll use the same function for validation and testing, but since we don't have a way to tell whether it's validation or not, we'll just call it loss and accuracy and print that out outside when we call them. Okay, so that should do it. Validate on dataloader model criterion, print validating, and testing. Cool. So now we have our stuff implemented, the whole pipeline implemented, or not. So this error happens inside validate and line 79. Sorry, what? Line 79 module object is, oh, my bad, it's not called, oh, sorry. Yay. So we have the, okay, so we have something like this. So for a given epoch, it's first gonna train the model, print the training loss accuracy, print the validation loss and accuracy, then the testing loss and accuracy. Okay, so we are almost done with the tutorial, except what we are missing right now is, we don't have a way to save the files. So saving files is helpful. So in your assignments, I asked you to always implement inference script. So saving files will also allow you to do things like transfer learning. So for example, if you save a checkpoint and then your training breaks in the middle for some reason, and then you were not saving any checkpoints, then you'll essentially need to start your training from scratch. So that's why you need to save your checkpoints, so that if something breaks or if you want to resume your training later on, you can do that. Now let's see, let's create a folder called checkpoints, and well, saving a model is pretty easy, and I'll reduce this to just one epoch even. Saving is quite easy in PyTorch. We literally just have to call this torch.save method on any object that you would like to save. Now what do we want to save here? The model's state dictionary. So this torch.save is, it's like a pickling operation, but it's better than that. And this is the object that we want to save. We can also save the optimizer's state dict, and let's actually see what this looks like to give you an idea. Okay. So you see the state dictionary of the model contains all the different things in our model and their saved values, like trained values until that point. So we want to be able to save these guys. You can do the same thing with the optimizer, and save the optimizers checkpoints as well if you want to save them. But for this tutorial, we'll just save the model itself. Checkpoints dot not LSTM model.pt, and that should be, oh well, any save function is incomplete without its corresponding, I guess, load method or load function. We can write it here. Let's write it here. Save checkpoint, it receives a model and then it does this. Then we'll also need to write a load model. Actually, we'll do that in the inference script. Let's write the inference script now. Let's call it train, or main was also fine. I don't know why I changed it. Inference.py. Now here is where we load the model. Load the model and then run predictions. So I'm just going to show you how to load the model, like actually running the prediction. It's the same thing as, it's very similar to like testing and validation. So and we can get rid of this now. Definition, load checkpoint, so the name, CP path, so similar to torch, torch.save, we have torch.load. So when we run this torch.load on whatever's in this CP path, it's gonna load the object. So right now it contains the state dictionary of the model, right? So we'll actually need to apply these models to whatever, like we'll actually need to create a model, is what I'm trying to say here. So to do that, we'll need to first of all create an instance of the model, and let's also do one thing. Yeah, let's move this classifier from here to, another thing you can actually do to make your code more modular is add this train and test as like a method inside this LSTMClassifier class. So have something like train or whatever, and then it does the training, and similar for validation, and then you can also have something like a predict method. So that will make your code look nicer, and it will be easier for you to manage. So now what we can do is, here we can import our LSTM from models, import LSTM class, and LSTM classifier, it's gonna be vocab size. So okay, so here's where the catch lies. We are not saving the vocabulary. Oh, okay, interesting. So let's also save the vocabulary. That's a good idea. With open data word. Pickle.dump word to index in this to this file. We need to import, we need to import pickle, and now we should also, and we will basically load that. Oh yeah, for sure. We have this though. From models import LSTMClassifier. Okay, cool. So now we have this, and we should at least be able to get the vocab size. Word to index is equal to well, this is, by the way, not a good way of doing this whole thing. There's probably a better way to not repeat these operations as much, but for now I'm just gonna go with this word to index.pickle, and I'm gonna read it. And the vocab size now is gonna be word to index, and embedding is, I know it's 300, 512, n layers, 2 classes. Now this is the checkpoint. Now what you want to do is you want to load this state dict. So this is torch.load is going to return you the state dict, and then when you call it on top of the model, you will be able to actually, so that's your load checkpoint. And I'm not going to finish this whole script, but yeah, once you have loaded the model, it's essentially doing the same thing as here. You get the you make a data sample. So here you'll need to make a data sample which will have, like, you know, those input IDs, something, and then I guess that's all you will need to have. Or oh, okay, actually my bad. So you should here, you can just start with a sentence. Let's say I like this restaurant, and then on top of this X you need to apply whatever pre-processing you did in your data loader, and then get that batch, that dictionary with input IDs, text, and blah blah blah, and just pass it through the model like so, as you're doing that here in this test method function, sorry. Except you'll not be using a data loader, you'll just need the model, and yeah, you will be able to get the predictions in real time for your deployed system. So, you know, let's finally remove this, because I want to show you one last thing before we call it a day. So this is the training loop. So now it's taking time because it's processing all the 800,000 sentences. And okay, as you can see, it's showing me like about half an hour for one training epoch, and that's quite slow. And the reason for that is because everything is happening on a CPU right now, so we need to move things to the GPU. Let's do that. That's quite straightforward. So device CUDA, if torch.CUDA is away, so if the CUDA driver is detected, it's going to be CUDA, else it's going to run on CPU. So this code is going to be executable from, you know, both your, even if you're Mac, I guess, or your Windows local Windows machine. It's just going to take a bit longer, as you just saw. Now once we have this device, we will actually need to put our tensors there. So these guys need to be on the tensor, on the GPU. Or to keep things simple, actually no, let's add it here. It's gonna save us some time overall. Labels can stay on the device And we probably need to add this device Amazon review dataset here. Cool. Device. Alrighty, now all we need to do is this. Okay, so we put our input tensors. Now we also need to put our model on the GPU. This should hopefully work. Okay, so somewhere it found a discrepancy right here in the logits and why. Oh, so the logits are on the CPU, but these guys are on the. So let's also, where is it? So until now it was a tensor, sorry, it was an integer, but since we want to put this, since we want to call this to method, we'll need to convert it to a tensor. And okay, voila. So we were able to reduce that training time, projected training time at least, from half an hour to a few minutes. Now, you know, this can further be reduced. Let me show you how. So there are two ways. So this is the naive way of implementing an LSTM classifier. Now, if you remember, we added a lot of padding tokens to it, and then there exists something in PyTorch that we can utilize to, you know, implement a more logical or a more smarter way of doing this forward pass, so that we ignore those padding tokens altogether. So that thing is called pack padded sequence, and its counter equivalent. So what it does essentially is it packs it quote unquote packs an input tensor that's already padded, and it also accepts the lengths of the inputs, right? So this is how it decides that anything that comes after that comes after this ID in a given sentence, it's not going to be useful, right? So we almost have everything to implement this, except we don't have this length. So let's compute that as well, and that's quite easy to do. We can do it right here inside this text to indices. So when we are doing blah blah blah, I guess, yeah, I guess what we can do is we add this EOS, and text length is equal to length of input IDs, and for the other case it's gonna be text length is equal to length of input IDs again, and we will return this text length, and text length is gonna be, well, we are getting text length and we should now have this attribute there. Where's the model? So, you know, for let's reintroduce these guys to make sure it works first, and then Okay, so once we have that, what we basically need to do is we have this embedding matrix, embedding vectors for all the guys. So what we need to do now is we need to pack them. We will, so what's the call? Torch nmutils, torch nmutils rnn pack parent sequence. So the input tensor here is going to be embedded. The lengths gonna be text. Actually, let's just call it length. Okay. Length, and enforce sorted is false. So by default this parameter is true, and if we keep it true to true, it will expect that this embedded or this input IDs, this X of input IDs is sorted by like decreasing value of their lengths. So the first element in the path should be the longest and the last one should be the shortest. But later on in PyTorch they introduced this thing, so it's not required now. So this is the packed, so we kind of code packed it. Now we will pass, instead of the embedded thingy, we will pass this guy, and so let's see what this. So if you look at LSTM's documentation, that then if you input it a packed padded sequence, then it's gonna return a packed padded sequence as well, a packed sequence as well. So we can actually look at it right here, intercept it. Oh, my bad. Okay, let's look at this thing, self.rnn. Oh, I see. So I'll need to, since there's a script already running on that GPU, we saw that error. Okay. Oh, I see. Let's just run it on oops. Let's try running it on a CPU. This is for debugging purposes anyways. Maybe VS Code doesn't support. So there's a bug. So the bug is indices element is out of data bounds ID. Actually, let's also, okay, just to be cool. So now we have this thing. So instead of, if you remember, we had a tensor before, used to have a tensor before, now we have a packed sequence, and this packed sequence is a funny object. So if you look at this packed sequence, it contains a lot of things, and you'd expect that this data is what we would need. However, this is weirdly shaped, and that's because it's packing all the different sentences of different lengths. So that's why we need to basically unpack this. So how do we unpack it? So again, this is the packed output, remember, and in this case, let's do something. I'm gonna not completely remove this. So okay, and so that we have this version as well. So now so this is forward, no packed, simple. So now I was gonna unpack this guy. So how do we unpack this guy? We use the opposite method of pad sequence. That's pad pack sequence. Yeah. So although it says pad in the name, all it's doing is it's kind of unpacking stuff, and it accepts the padding value. And okay, let's see what it outputs. By the way, it returns a tuple of tensor containing the padded sequence, a tensor containing a list of lengths. So we only need the first object, I guess. So we'll ignore the other guy again. Okay, sweet. torch.nn.utils.rnn.pad packed sequence. We pass it the output, and it also accepts, oh yeah, of course, patch first will be true, but it also accepts the padding value. Now I can go with a if we go with the config file, we won't need to hard code this value like right now, but we don't have such a luxury. So I'll just hard code that padding value to what it is in our dataset. That's 2. And batch first. So when I do batch first, it's gonna put the batch dimension as the first dimension. It makes things easier to process. Okay, so let's see what we get after running this guy. Oh, output is not defined. Output of now. Oh, okay. You know what? I'll just rerun this. Some weird issue. Let's see. All right. So this is the unpacked output, right? And if you look at the shape of it, it's gonna be 64 by 27 by 512, and we got this by essentially doing that length thingy. We passed those lengths, right? So how do we actually make sense of this thing? So when it returns, because we want to again go from BS to T to 300 to BS to 2 essentially, so we need to construct the feature vector here. And constructing the feature vector in this case, it's not really as straightforward. I mean, it is if you kind of understand what's happening under the hood. So we'll again be doing tensor slicing, but this guy won't do now, because since we tried to optimize stuff, we cannot know beforehand what's the I guess length, what's the value of the second index. So what we want to be doing here is, for every element in the batch, for that ith element, we'll be basically we did have the length, right? So we can use this length because we know that for that particular element, this is the maximum value, like the index of that maximum element that we are gonna be needing, and this is gonna be our feature instead now. And if we apply this, oopsie, and if we apply this operation here, voila, we got this. And let's also look at the values. So yeah, so actually let's see what happens if let's try to do what we were doing before. So as you can see here, it's literally just getting those padding padded IDs, padded sequences, like those padding tokens, and its shape, how by the way, it's this, but you know, it's also, so that's why it's important to not only match the shapes but to understand what's the value of the object, understand what's going on. So here what we are doing is, for every element we are basically fetching this ID'd element, otherwise it was just gonna fetch the padding token for us. Now it should be fine, and hopefully we see some speed up in the training process. Let's see. Bye bye. So actually let's also increase this guy. Oh, it's, sorry, my bad. It's, everything's happening on a GPU again, sorry, CPU again. Waiting. And voila, what do we have here? So if you remember, we went from half an hour to something like 8 minutes to something like 3 minutes. So I mean, this task is pretty easy, so it will be difficult for I mean, it's just a few minutes per epoch, but if you scale it to larger models, it's gonna save you maybe even months or days of training. And I guess one other thing also that would happen is your model is going to learn faster. It's not going to be very evident in this case because, you know, like it's a binary classification task, and well, the model is too expressive right now, like it has so it's not going to be very visible, the difference in performance, but this guy is going to learn faster than the other guy, and it runs faster than the other guy, so why not? So that concludes this lecture, and I hope you found, not lecture, sorry, this tutorial, and I hope you will find this video useful for your assignments. And yeah, feel free to play around with these hyperparameters, and I'll be uploading this code somewhere. I'll add the link to. Thank you. And sorry, this turned out to be a bit long.